Good morning, everybody. I'm Julen Expósito, and I have been working in the project of high-performance data analysis, global simulations of the interaction between the solar wind and a planetary magnetosphere. The group with which I have been working used the parallel code for kinetic multi-scale simulation of plasma's EPIC3D. This code is a particle-in-cell code, so we have the simulation defined in a box separated in different cells, each one with physical quantities associated, as magnetic or electric fields, and then each cell has particles in its interior, with positions are being updated at a greater spatial resolution. The user can decide what information he wants to be stored in files and at what times. These files can take up teras and teras of space. Usually, a post-processing is done with these files that end up resulting in much lighter datasets, which contains processed information that will be analyzable and suitable for comparison with observational data. Part of this post-processing could be implemented within the code itself for the resulting files from running the simulation to be directly the ones that contains the information you're looking for. That way, you can avoid having to save and work with extremely heavy files, and the whole analysis process is accelerated and simplified. This is what I have been doing for the last 2 months. I have been focused on implementing 2 post-processing routines directly in the code, one that stores the temperature tensor in its cell and one that stores the energy spectrum of the particles at each point in the space. For the first routine, we know that we can obtain the temperature from the pressure. The code already gives us the pressure tensor in the form of 6 different files, each with the value of one component in each cell. What we want to do is to define this tensor in a coordinate system that interests us, in this case, one relative to the local value of the magnetic field, and then transform it into the temperature tensor. For this purpose, I have made a base change to the tensor. I don't have time to go into details, but the idea is basically to define a new coordinate system in which one direction is parallel to the magnetic field and the other two are perpendicular, and then make a rotation to the tensor to define it in that new coordinate system. Then we perform a second rotation, forcing the 2 perpendicular components of the diagonal to have the same value. This facilitates the study of the aerotropy of the system at that point. Finally, the change to the temperature tensor is direct considering ideal gas. We end up with an unique file instead of 6, facilitating the analysis when using a data visualization and analysis program, which contains the values of all the components of the temperature tensor in each of the cells of the simulation. The second routine is a little more tricky. Observationally, we can obtain information about particles in the form of an energy spectrum. That is, we can know how many particles have one energy or another in different directions. The code, on the other hand, stores files with data on the positions and velocity of each particle, which takes much more space. This routine will use that information to create the energy spectrum and will only create a file with that exact information. For that, we have to count the particles that have energies within different ranges. This routine asks the user to define the energy bins with which he wants to define his spectrum. Once that is done, it only remains for each MPI process, which will deal with a specific volume of the complete box of the simulation, to pass through all the particles inside it. For each particle, the process looks for which cell it belongs to, perform the same change of coordinates to its velocity vector as we did before, to have the velocity component parallel to the magnetic field and 2 perpendicular components, use those velocities to calculate the kinetic energy, and then places the particle in the energy bin that corresponds to it. In the end, we end up with an array of n elements, where n is the number of energy bins per cell. These elements tell us how many particles are inside each bin. Here you can see the result for a random cell. In a simulation where the particles are uniformly distributed with an initial thermal velocity in their direction parallel to the magnetic field 3 times higher than the thermal velocity in the other 2 directions, the x-axis corresponds to the energies and the y-axis to the total charge found in each bin. Constructing this spectrum was a cumbersome and expensive process in the past, but now anyone using the code can directly request it as output. And that's it. I hope these new routines will make life easier for future users of the code. Thank you for your attention.